Think about how we usually make things cold. It is a loud, physical process. We rely on compressors vibrating, churning chemical refrigerants, and pumping heat out through brute mechanical force. But there is another way. Apply an electric current to a solid-state Peltier tile, and frost instantly blooms across the smooth ceramic. There are no moving parts, no motors, and zero noise. What you are seeing is the direct manipulation of entropy. By forcing electrical charge carriers across microscopic junctions between two different materials, heat is absorbed on one side of the tile and expelled on the other. Achieving cryogenic precision in absolute silence contradicts almost everything we experience about how temperature control is supposed to work in our daily lives. Yet, for all its elegance, this technology has carried a crippling historical constraint. Despite the physics at play, these tiles have long been limited by severe energy inefficiency. Feed 1 joule of electrical energy into a traditional solid-state system, and the output shrinks down to just half a joule of actual cooling power. Compare that to a standard compressor refrigerator. Vintage models operated at high efficiencies, leaving solid-state alternatives at roughly 1/8 the efficiency of mechanical rivals. That energy penalty is the primary reason our modern world is still cooled by loud, vibrating motors instead of silent, solid-state plates. To understand why that penalty exists, we have to look past the macroscopic ceramic plate and examine the microscopic architecture sandwiched underneath. Inside a tile are alternating pillars of P-type and N-type semiconductors, linked by thin metal bridges. Applying a voltage manipulates their energy levels. This creates a kinetic bucket chain, forcing thermal energy to flow continuously in one singular direction. But this forward momentum immediately triggers a fierce physical reaction known as the Joule effect. Think of the Joule effect as a frictional backflow. As electrons travel through the circuit, they crash into the rigid atomic lattice. Every single collision generates a localized flash of heat. Here lies the paradox of the system. The exact electrical current required to drive the cooling bucket chain simultaneously generates frictional heat that bleeds backward, actively fighting the cold you just created. By 2026, the thermal demands of high-performance computing have reached a critical threshold. As AI chip clusters and quantum processors generate heat at increasingly microscopic scales, traditional fans and liquid pumps are struggling to scale down to the required precision. Managing these systems requires pinpoint thermal control that only a solid-state architecture can deploy. A major step toward that precision occurred in 2015, when a joint US and South Korean research team found a way to block thermal backflow using a specific bismuth antimony telluride alloy. They developed a manufacturing technique called liquid flow assisted sintering. Solid metallic granules are fused under intense heat and pressure, while excess liquid tellurium is forcefully squeezed out from between them. This intense physical compression leaves behind dense dislocation arrays embedded tightly within the grain boundaries of the alloy. These structured boundaries act as a physical sieve, scattering backward-moving heat phonons while allowing electrons to glide cleanly. This efficiency spike is shown by the data curve rising sharply, breaking past a peak ZT of 2.01 at 320 Kelvin. By physically engineering the seams between microscopic grains, researchers successfully trapped the frictional heat without choking the electrical current. That materials engineering evolved again in 2020. Researchers shifted away from forging bulk alloys and moved toward depositing highly precise antimony telluride thin films. They built these films atom by atom, using a complex technique known as electric field-assisted magnetron sputtering. The crucial variable in their experiment was applying an exact 30-volt external electric field to the substrate while the film was actively being deposited. That 30-volt field forced the incoming particles to align differently, locking the intraplanar grain boundaries into a precise 30-degree angle. This specific geometry triggers a process called energy filtering. The 30-degree tilt severely weakens phonon hole scattering, suppressing heat transfer while preserving incredibly high electrical carrier mobility. At standard room temperature, this tilted architecture achieves a high ZT value of 1.75. By using invisible electric fields to sculpt the angle of a crystal, science bypassed the Joule effect to achieve high-efficiency cooling in standard conditions. When we pull back from microscopic grain boundaries and efficiency metrics, we can see the macroscopic potential of these scientific victories. For decades, the severe energy penalty kept solid-state cooling trapped in laboratory environments, treating the technology as an experimental curiosity rather than a practical tool. Removing this efficiency barrier changes the economic viability of solid-state systems. It moves the technology from niche research applications toward integration in high-volume consumer appliances. This performance jump provides a roadmap for the transportation industry to reconsider climate control. In electric vehicles, where every watt of battery power and every pound of weight is critical, solid-state tiles offer a path toward localized cooling without the need for mechanical pumps or moving parts. The concept of thermodynamic control is transitioning from the loud, vibrating mechanical process into a purely silent electrical phenomenon. By engineering materials down at the nanoscale to win the thermodynamic tug-of-war, we have taken Peltier tiles from inefficient novelties and forged them into the silent cooling engines of the future. Dive deeper into the hidden secrets that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation, only on TemboDocs.